Okay, welcome back. Um, all right, before I begin, any questions? Everybody knows what's coming up on next Tuesday, right? Exam number 1, chapters 1 to 3. If you've not checked or downloaded the Lockdown browser, you need to make sure you do that because you cannot take the exam without the Lockdown browser. Now, here's a couple of things about the Lockdown browser. It seems to be functioning differently depending on computer system. What it is overall is it's a separate browser all by itself. Unlike the Chrome browser, this browser is specifically made for the Maricopa schools. Okay, and so what that does is basically lock you out from accessing other online sites, and it keeps track of if you are going someplace. It would tell me where you're going. All right, but so normally what happens if you click on the assignment that requires a Lockdown browser, then automatically the Lockdown browser is activated, and then you do the quiz or whatever you got to do. Okay. For some systems, I don't know why, but for some systems, you actually have to, once you download it, it creates an icon on your desktop, and then you actually have to first just click the Lockdown browser icon itself and get that going. Because if you click the assignment for whatever reason, it may not activate the Lockdown browser. Okay, so check your system. I think most of you already gone through it. It works for you, not a problem. And then once you get, you click on the Lockdown browser, you log in like you normally do, and then you go to the assignment that you need to do, and then it allows you to complete that assignment. So only the homeworks, not the homeworks, only the exams, the 5 exams require the Lockdown browser, including the extra credit, which is just a check to see that the Lockdown browser is functioning properly. There's about 4 or 5 you have not done that. So really get that knocked out before next Tuesday, okay? All right, any questions? I was asked about the homework assignment. Where's that now? Remember, if you look at the course, it's laid out in modules. And every chapter that we do has its own specific module. And within the module has all the resources you need for that particular chapter, the textbook, the worksheets, videos that were pre-made. They're not the videos that we record here, but those were created by Dr. Kim in GCC, where she talks about the topic that we talk about. Okay, so you have another resource there to listen to someone else present the topic, and then of course you have the videos that we record here that are uploaded to the YouTube. Okay, so a multiple of resources for you. All right, so let us finish up with the chapter that we started. I only have a few more slides and we'll be done with this one. We were talking about, we actually stopped on page 22, but just to refresh your memory, we're asked to write the notation, the atomic notation for bromine 81. And the format is as follows. You have the symbol, okay? Okay, you have the symbol. Oh no, bear with me, I'm having trouble with my pointer here again. Oh, there it is. Okay, and so we have the symbol. I thought I had it. Not working now. Okay, it is. Whoa. which is the letter SY is the symbol, okay? And every element has a symbol, be it a single letter or a two letters. The first letter always is capitalized, second letter is always lowercase. Then in the upper left corner, upper left superscript, if you will, is what is called the mass number, okay? The mass number. That is always, remember this, this is always a whole number, okay? Because it is the sum of the number of protons and the number of neutrons for that particular element. And then in the subscript, left subscript is the atomic number, okay? And that is specific for that particular atom, whatever the element, whatever it may be. Every element has a unique, there's 118 atomic numbers. That represents how many protons and how many electrons that element has. So bromine, you'll see, has an atomic number of 35. And they're asking you here, okay, write the notation for bromine 81. And we talked about, why is that the most abundant isotope? Remember that these elements, there's more than one type of, say, carbon element, okay? There's carbon 11, carbon 12, 13, and 14. All of them are carbon. Where they differ is the number of neutrons that they have, okay? Now, everyone has their own specific mass number. So the mass number is given to you here, and it says bromine 81. So there's the mass number. You don't have to look anything up in the product table. It's given to you. So automatically that goes in the upper left superscript, okay? And then 35, well, you need to go look for bromine on the product table and find its atomic number, okay? Now, the difference between the mass number and the atomic number represents the number of neutrons, okay? So 81 minus 35 is 46 neutrons. So bromine 81, okay, has 46 neutrons. So let's summarize what it has. Let's talk about bromine. The number of protons that bromine has is positive, is 35, okay? The number of electrons at bromine 81 is 35. The number of neutrons, in this case for bromine 81, is 46, okay? The sum of the mass number and the atomic number, the sum of the neutrons and the number of protons give the element its specific mass number. Okay. Now, we were talking about, is this the most abundant isotope for bromine? Well, to answer that question, we go to the periodic table and we look for bromine. Bear with me. Zoom is acting up today. Okay, we look for bromine. Bromine is right here, number 35. Okay, if we look at the atomic weight of bromine, it is 79.890. If we take that number, that decimal number, and round it up to the nearest whole number, we end up with bromine 80. Okay, and bromine 80 is the most abundant isotope. In this example, they were asking about bromine 81. So bromine 80 is the most abundant isotope. Sorry, my resolution for some reason has gone crazy on my mouse. So that's bromine 80, okay? Two types of bromine, they both have the same number of protons, they both have the same number of electrons. Where they differ is the number of neutrons, okay? And the reason we can go to the periodic table, look at the atomic weight, round that number up to the nearest whole number, and that tells us that is the most abundant isotope is because we have two types of bromine, bromine 80, bromine 81. In nature, bromine 80 there's more of abundance of bromine 80 than there is 81. Okay. And so that decimal number, the atomic weight, is a average of these whole numbers, a weighted average. So if bromine 81 exists like 90% in nature, we have to account for the fact of that 90%. And so that 80 plays a larger factor in the overall average than say 81, okay? So these are weighted averages. The atomic weights are weighted averages of all the isotopes of that particular atom or element, I should say. Okay, let's clear this up. All right, so isotopes. I mentioned this before. We're only listing 3 isotopes here of carbon, but there's really 4. Carbon 11 is just a trace amount. And so here they're giving you the mass number. We got carbon 12, carbon 13, carbon 14. Okay. Question is, how many protons do each of the carbon have? Well, all carbons here, all these isotopes of carbon have 6 protons. Remember, the protons defines what the element is. What is differ is the number of neutrons. Okay, so carbon 12 minus 6 leaves 6 neutrons for carbon 12. Carbon 13 minus 6 leaves 7 neutrons for carbon 13. And carbon 14 minus 6 is 8 neutrons. So the difference between carbon 12, carbon 13, carbon 14 is simply the number of neutrons that it has. Okay. And the most abundant isotope that's in nature is carbon 12. And that's why if you look at the periodic table and you see the atomic weight as 12.01, that's because carbon 12, there's roughly 98, 99% of carbon 12 in nature. So its contribution for carbon 12 is much greater. If we were to average these 3 numbers, 12, 13, and 14, obviously we get an average of 13, okay? But when we talk about a weighted average, since there's more carbon 13 in nature, there's going to be more carbon 12 that contributes to the overall average. And when we do all this and account for all the contribution for each isotope, we end up with this average of 12.01, okay, which is closer to carbon 12. That's why we can take the atomic weight and round it up to the nearest whole number, and that tells us the most common, most abundant isotope for that particular element. All right, so let's look at oxygen. Okay, we get 3 isotopes of oxygen: oxygen 16, oxygen 17, and oxygen 18. The first question says, what is the mass number? Well, it's given to you. It's that number right after the hyphen. Okay, so the mass number is 16, 17, and 18 respectively. Now, with respect to protons, well, they're all going to have the same number of protons, okay, because that's what defines oxygen, 8 protons. And they're all going to have the same number of electrons, okay? What's going to differ is the number of neutrons. So it is the mass number minus the number of protons gives you the number of neutrons. So carbon 16 has 8 neutrons, carbon 17 has 9 neutrons, and carbon 18 has 10 neutrons, okay? All right. All right, so this again is a rehash of why we can take the number, the atomic weight on the periodic table, and then be able to define or determine who's the most abundant isotope. Again, here's the example of carbon 11, 12, 13, and 14. Carbon 12 is roughly 98.89% in nature and about 1.1% for carbon 13. And then there's trace amounts of 11 and 12. And so, if we average out these whole numbers, 11, 12, 13, and 14, the average of those four numbers is 12 and a half, right? 12 and a half. But then if we incorporate the percentage that they contribute, you'll see that 98.89% consists of carbon 12. So the carbon 12 contributes more to the overall average than the others, 11, 13, and 14. And when we take the weighted average of these four isotopes based on their contribution and their abundance, then we end up with a weighted average of 12.01, and that is the atomic weight of carbon. Okay. And again, this is why we don't use the atomic weights as determining factor in sig figs, because the atomic weights come from whole numbers. Okay, and the weighted average of these whole numbers results in having an infinite number of sig figs. So we don't utilize the atomic weight in determining significant figures. All right. Now, this type of a question, they're asking you, okay, lithium-6 versus lithium-7. Which is the most abundant isotope there? Well, to answer the question, you go to the periodic table. Okay. Notice I make reference to the periodic table a lot. There's a lot of information on this periodic table. Right now, what you see is just a table, but we're going to learn so much information that what's in that table to help you with the chemistry overall. All right, let's look up lithium. Lithium's sitting right here. Let's zoom it up a little bit. Zoom. Oh, come on. Lithium's number 3. Okay. It has an atomic weight of 6.94. So if you take that, round it up to the nearest whole number, you end up with lithium-7. Lithium-7 represents the most abundant isotope of the lithium isotopes. Okay, what about chlorine-35 and versus chlorine-37? Which one is the most abundant isotope? What do you think? Okay, so use the periodic table. Go look for chlorine. Okay, find its atomic weight, and run it up to the nearest whole number. Okay, chlorine is right here, number 17. It has an atomic weight of, you got it, exactly. So it's chlorine-35, which is the most abundant isotope. Okay, and so given the periodic table, one word about the periodic table, we have much more to say about that as we use it quite often. A lot of these numbers are in decimal numbers as far as the atomic weights. That's the number underneath the symbol. However, you see some numbers have a parenthesis in their whole numbers. And the reason they're whole numbers is because they're radioactive and they break down very quickly, very readily. And one can't really get a true atomic weight. There's not enough information about it. So they put the atomic weight on with parentheses, which means that it's going to be very difficult to determine the most abundant isotope. But if I had to determine the most abundant isotope for number radon for number 88, I would have to say radon 226. Okay, leave it at that. But all the other ones, they have decimal numbers. You can readily, easily round it up to the nearest number, and it gives you the most abundant isotope. And you don't have to memorize anything, just know where it's at in the periodic table. And that's what I was saying here about elements. Some elements are radioactive and very unstable. You'll find those that have parentheses as far as their atomic weights, like curium 247, or element number 96. That one was named after Madame Curie. And I don't know, as a side note, Madame Curie was quite the scientist. A lot of people think she was from France, but that's not the case. Her husband, she went to France to get an education because in her homeland of Poland, women were not allowed to get a higher education. So she left Poland, went to France during that time period. France was the mecca of science and so forth, and got her doctorate there, and ended up with two Nobel Prizes. And her kids also ended up with a Nobel Prize. So quite the family. All right. We're going to change tracks a little bit and introduce you briefly to chemical formulas. Now, what these represent are at this point in time, we don't know the names. We're not going to learn that, but we want you to recognize the number of atoms total within a chemical formula that we put in here, okay? So it's not going to tell us anything about the bonding order or how it's put together, anything like that. Remember that the subscript tells us how many of those atoms of whatever atom you're working with, like H2O. H2O, the formula H2O says H2O says that there are 2 hydrogen atoms and 1 oxygen atom. Okay, so there's a total of 3 atoms in a molecule of H2O or water. Okay, and that's what we're going to start learning here. Now, when there's no subscript, just it's understood as a 1, just in mathematics. It's understood to be a 1. Okay. All right. All right, so here we go again. H2O is an example of 2 hydrogen atoms and 1 oxygen. Doesn't say much about the bonding. We're going to learn about the bonding order. Generally, what we're going to learn is that we're going to have like 1 atom, which is the central atom, and then everything around it is bonded to the central atom. Okay, we're gonna start learning about that, but not right now. Okay, so let's take a look at this particular formula. You see the formula here given to you is C3H6O3. Okay, not really concerned about what that is. We want you to recognize that there are 3 carbons, 6 hydrogens, and 3 oxygens. Okay, for a grand total of 12 atoms. Eventually, we're going to take that information and utilize it to break down and figure out the percent composition of a compound. Every compound has a percentage. There's a percentage of hydrogen, percentage of oxygen, percentage of carbon, and we're going to be able to calculate that. But in order to do that, we have to first recognize and understand how many atoms we are talking about. Okay, and recognize that they're different. So we got 3 carbons, 6 hydrogens, and 3 oxygens for a total of 12 atoms. Now, sometimes you find chemical formulas with parentheses. Okay, now here's something important about this. When you see a formula with parentheses, what that is telling you is that what's inside the parentheses, specifically NH4 here, are units that we keep intact and together. We don't separate them. And if we need to have more than one, we use parentheses and then a subscript. So notice in this example here, well, let me send you to this NH4. If we go to the periodic table, we're going to utilize these units, as I call them, quite often. You'll find it on the periodic table, specifically on the left side where it says most common polyatomic ions. And the one we're looking at right now is NH4, okay? But there's a whole series of different ones. And we keep them together as a unit. And if we need to add more than one, we put a parentheses around it. Each one of these units, okay, or polyatomic ions, has their own specific name that does not change. Keep that in mind when we start talking about nomenclature, naming compounds. And so the one with NH4, we're talking about with a polyatomic ion that is called ammonia, okay? And then we have such things as acetate, hydroxide, cyanide, etc. All right, so if we look here, we see that we have in parentheses NH4, the ammonium, and specifically there's two of them. So there are two ammonium units, okay? Which means that there are a total of 2 nitrogens and 8 hydrogens. See how that works? There are 2 nitrogens and 8 hydrogens for the 2 ammonia units in parentheses. And we have 1 carbon and 3 oxygens. And so overall, we got 2 nitrogens, 8 hydrogens, 1 carbon, 3 oxygens for a grand total of 14 atoms in this compound. And I'll give you the name for this guy. This is called ammonium carbonate. Ammonium carbonate. The one we did before earlier, C3H6O3, that's a general formula for, if you like Italian dressing, you're eating a lot of this. This is acetic acid. Acetic acid or vinegar, aka vinegar. All right, so here recognize how many atoms, individual atoms you have. This is the purpose of this exercise here. Okay, we're going to learn how to use that information at a later date. Okay, here's a couple more examples. Okay, understood? You don't know what they are, or you may know, but that's okay. What we want to know is simply how many atoms are in each formula, okay? I'm going to tell you what these species are, but we will talk about that in here in a bit. So if I look at H3PO4, we'll see that we have 3 hydrogens, okay? 3 hydrogens. Okay, 1 phosphorus and 4 oxygens. Okay, let's do it again. We got 3 hydrogens, 1 phosphorus, and 4 oxygens. Okay, whoa, 1 too many. If we look at the next one, so we have a total of 8 atoms for the first one. The second one, we have 1 calcium, okay? Then we have a parenthesis. Here's one of these units, these polyatomic ions that we use parentheses to show that we need more than 1. So there's 2, there's the subscript 2. There are 2 hydroxide that has its own name, hydroxide. If you look at that table for polyatomic ions, you'll see the OH polyatomic ion has its own specific name called hydroxide. And in this case, there's 2. And we're going to learn why there's 2 for calcium. We certainly will learn why. I mean, there's a reason why there's 2. So we have 2. That means we got 2 oxygens and 2 hydrogens for a grand total of 5 atoms. So you got 1 calcium, 2 oxygens, and 2 hydrogens, grand total of 5 atoms. Now, in this particular one, a little more challenging, but not really. Here we got 2 aluminum atoms, okay? All right, now, then we have the parentheses again. So this is the unit. And this particular name is called, the unit is called sulfate. Sulfate, check the polyatomic ion table to see that. And specifically, there's 3 of them, okay? 3 sulfates around the parentheses, which means that there are 3 sulfurs, okay? And a total of 12 oxygens. 4 times 3 is 12, okay? And 3 times 1 for the sulfur is 3. So we have a grand total of 17 atoms in that particular compound. Grand total. Okay. The first one, H3PO4, that's pretty common material, especially if you drink a lot of soda pop. That's called phosphoric acid. It's an acid. The next one, calcium hydroxide, that's called the base. And then we have aluminum sulfate. Okay. And you might guess, well, how do I know that name? Let's briefly show you how you can come up with that name for the last 2. Okay, calcium hydroxide and aluminum sulfate. All right, now point number 1. We know that Ca is calcium. We know that Al is aluminum. So that's the first name, calcium and aluminum respectively. We look up the OH, it's a polyatomic ion, and we look up the SO4, okay? And where do we look that up? We go through the periodic table. Oh, there you go. Okay, we have SO4, which is sulfate, okay? And then the OH, which is called the hydroxide. Okay, so with that in mind, we know the name. If we have to put it together now, we go back to this, and we have calcium hydroxide and aluminum sulfate. Okay, and it could have been calcium sulfate. We can do mix and match. We're not stuck with just calcium hydroxide. We're going to eventually be able to mix and match with, say, potassium hydroxide, sodium hydroxide, and maybe even make it potassium sulfate, sodium hydroxide. We can create alternative compounds, and we can start building up a little database of all these chemicals that you put together by knowing the pieces and putting them together properly, right? But right now, I'm just giving you the name of it because there is a specific manner and a reason why there's 3 sulfates and there's 2 aluminums, okay? All right. So the law of definite composition states that when the compound comes together, they're going to come in with a proportion by mass. So H2O, for example, water, if it undergoes analysis, will always come back and show that there is 11.2% hydrogen in that molecule of water, and that oxygen consists of 88.8%. And that is true for any water molecule that you find anywhere in space or anywhere on Earth, okay? We will learn to do percent calculations at a later date. All right, so congratulations, we are done with chapter 4. What I want to do is I want to go to the, and make sure I got, close this. I want to go to the course website. Okay. And there is a resource for you, okay? Underneath the 3rd module, and there's the welcome, the first steps, and then there's additional chemistry resources. I did briefly mention this in the first day of class, but here's one resource that you can utilize to help you grasp and understand the concept of what we have at this point and how elements are put together, how the atom is put together with respect to protons, electrons, and neutrons. So if you click on build an atom, it's a simulation, okay? Give it a minute or two to get going, and just select the first choice atom. Okay, now, if we look at this, you will find that we have two little buckets here of protons, neutrons, and electrons, okay? Also note that there are a dotted line here. We got dotted circles, okay? We're going to learn that this is where the electrons are occupied. And we're going to learn that these dotted lines represent specific energy levels where the electrons exist, okay? Anyway, let's grab a proton. If you grab a proton, put it in the center. In fact, you can put it anywhere near the element, let go of it, and it goes to the center because that's where protons exist. By adding one proton, you have created hydrogen, okay? If I take an electron, now I can put that in there and look where he went. I kind of let go of it outside the outside dotted line, but it went into the inside dotted line. And we're going to learn about these electrons that when they start filling up these energy levels, obviously they start with the low level and then work their way out. So this is hydrogen, okay? Hydrogen itself, the most abundant isotope of hydrogen is hydrogen 1. Hydrogen 1 has no neutron, but we have hydrogen 2, which contains one neutron. Notice that gray neutron, when I let go of it, it went to the center, okay? So this represents hydrogen 2, okay? Because the mass number is up to 2 now. And the most common isotope is hydrogen 1. You can see the mass number here, 1. When it picks up a neutron, it becomes hydrogen 2. And then there's hydrogen 3, okay? Which is, it bounces around a little bit. Hydrogen 3 is an isotope, not very stable, okay? Not very stable as compared to hydrogen 2, a little more stable, but that extra neutron kind of puts some stability. All right, so if I continue to add protons, I am in essence creating a different element, okay? And I have 4 protons, so I need to add 4 electrons. So give me a net charge of 0. So I need my net charge, okay? And now you can start adding beryllium, you can start adding neutrons, and that's going to vary depending on the isotope and so forth, okay? Now, we're going to learn about how these elements either gain or lose electrons. And when we do that, notice my net charge right now is 0 because I have an equal number of protons and an equal number of electrons. But the moment I subtract and pull out an electron, look what happens. I got a net charge of +1, okay? Net charge of +1. And if I add an electron more than what it normally carries, I have a net charge of -1, okay? And so what is being generated is what we call ions. And you put this in long-term memory. All metals, we're going to learn the elements, which ones are all metals. All metals always lose electrons, okay? Let me restate that. All metals always lose electrons. The converse of that is there's a group of elements that are classified as nonmetals. And all nonmetals gain electrons, end up with a negative overall charge. In both cases, they create ions. And that is what you are drinking when you drink your electrolytes. You're drinking these ions. That's what's in our body that's allowing us to send electrical signals from point A to point B. They're being sent because we have these ions in our solution, in our body. Okay. So anyway, play with this simulation and it'll help you to understand, hopefully, how the atom is put together. Okay, you won't be able to make all 118, but you can make quite a bit. Yeah, I think you go up to I forget, neon possibly. Anyway, any questions?
Which ones gain electrons?
Okay, metals, and we're going to learn what are called metals versus non-metals. Non-metals gain electrons. Okay. And metals lose electrons. And they end up, and when you lose electrons, you end up with a positive charge. When you gain electrons, you end up with a negative charge, like I was showing you here. Let me go back. Right here, I have a negative net zero, but if I gain an electron, keep track of my net charge. Right now, my net charge is zero. Equal number of positives, equal number of negatives. If I lose an electron, pull one out, look at my charge. It becomes a +1, okay? This is beryllium, it's a metal generally, this is what happens. But it's gonna lose two of them. Yeah, and the counter, if an element gains electrons, look at the net charge now. It has a negative charge. Because remember, electrons are negative in charge. And if I add more electrons, I'm going to pick up more negativity. I try to use the analogy in psychological terms, if you will, human terms, because, you have a person, for example, who loses negativity, loses electrons, become more positive, right? And the converse is true. If you pick up negativity, you gain electrons, you become more negative, okay? So anyway, any other questions? All right. This brings us to chapter 5, which is going to help us to understand the atomic structure. Okay. We got a little bit earlier when we looked at, if we call J.J. Thomson and the other scientists that helped us, or that discovered the neutron, Chadwick discovered the neutron, J.J. Thomson discovered the electron, and then Rutherford discovered the proton and the nucleus. So they started to give us a picture of how the atom was put together in our particular model, okay? And the point is, it's a model. And since this was put together way back when, it has undergone many changes. And so tomorrow, this model can change again. So, which is a good thing as we learn more about matter and how it behaves and reacts and so forth. Yes, our model has to change accordingly. But currently, this is the model that represents how atoms are put together and how these electrons are put in this area. Because remember, the picture we have up to this point is we have a very dense nucleus where the proton and the neutrons exist. Then we have the electrons somewhere around in some type of orbit, someplace, somewhere. That's the picture we have up to this point. Okay, so more scientists came in and started to refine the model. Now, in order to talk about it, we have to kind of talk about how light exists as waves, because we will learn that the electrons, remember the electrons, for all intents and purposes, their mass is equal to 0 because they're so tiny. Well, with a mass that small, they actually behave like light does, okay? And so in order to explain how these electrons are behaving, we kind of got to talk about a little bit about a light and how it exists as waves, okay? And so here's a model of light and how it propagates through space, okay, in these waves. So all light has what we call a wavelength. This is what this symbol is right here, the wavelength. And what that is simply a distance from the top of the hill to the top of the next hill. Now, it doesn't have to be the top of the hill. It could be the bottom of the hill to the next bottom of the hill. That distance is a particular wavelength, okay? You might be familiar with this. For example, radio waves on the car radio, okay? Very big radio, humongous, gigantic meters long wavelengths, okay? Then we have on the other end of the spectrum, wavelengths that are very hazardous. The radio waves are not hazardous to our knowledge, but X-rays and gamma rays are. And that's because they're very small. They have very small wavelengths, okay? All right. Now, the other part about this conversation has to do with frequency. So wavelength is the distance between peaks, if you want, or the trough, if you want. It can even be any position on here. So if I pick this position here, I pick the same position on the next wave. That distance is lambda. That's the name of this symbol, okay? And that is the wavelength of this light, electromagnetic, I want to call it electromagnetic radiation because it's not necessarily just light. When I say light, you think of this light here, but there's electromagnetic radiation that we can't see, okay? Totally different, but they have their own wavelength. Now, the frequency is the number of wave cycles that are completed within a given second. And you might be familiar with this already. For example, your computer operates in a certain frequency. You might have 2 gigahertz, okay? Your cell phone also operates with a frequency, and that is how many for 2 gigahertz, we're saying that it can do 2 billion calculations within a second. That's pretty fast, okay? Fairly fast. Not as fast as our brain, but still fast. And to give you an idea that back in the 80s, I mean, we were in computer systems, we were doing megahertz, thousands, and we're up to gigahertz, and we're slowly creeping up to terahertz. You know, so the speeds are getting faster and faster, which allows us to do a lot more with computing power. So the frequency is the number of wave cycles completed in one given second. All right, so now let's compare 2 different wavelengths. If we look at the top one, that represents, relative to the bottom image, that represents a low energy light. Okay, because if you look at the wavelength of the top one and compare it to the bottom one, notice here that this distance right here, well, from here to the top of the hill, okay, that's the wavelength from the bottom one down here, that distance, compared to this distance here. You can see the top one is much longer than the bottom one. And so the top one represents a low energy light. So it's a long wavelength, okay? And if it has a long wavelength, it has low energy and low frequency. Okay. Within a given time unit, there's going to be a lot more of the smaller wavelengths going through within 1 second than the top ones. So the frequency goes along with which wavelength you're working with. Okay. So the low energy would be a good example would be radio waves. Okay. Radio waves are very large, up in the meters. And by the most part, to my knowledge, they're not causing any health issues, okay? Whereas if you go to the other end of the spectrum, you have the X-rays and you have gamma rays. Those are very small wavelengths, very small. And they have high energy and high frequency and can be very damaging. X-rays go right through you. Radio waves, you can block radio waves. Your body can block it. Buildings block the radio waves. But X-rays, especially gamma rays, are pretty powerful. They can go through a lot of material. Okay. All right. Now, here they ask you to compare two different wavelengths. They ask you which has a higher energy. Well, that would be B, and the lower frequency would be A. Okay. Be A. All right. Now, here's the spectrum that we generally, and it's not to scale, but if you look in the middle there, it says the visible. That is what our eyes are capable of identifying and seeing. It's the visible wavelength, which compared to the spectrum is very tiny, okay, very small. Now, on the far right, you have the radio waves, which again are not high energy. And then on the far left, you have these gamma rays you find out in space that are extremely hazardous. We have the X-rays here that exposure to too many X-rays can cause issues. Okay, right below the visible, you have the infrared. Okay, and you have the ultraviolet. In both cases, we can't see them, but we do have instruments that allows us to observe in that particular wavelength. And then, of course, here we got the microwave over here. That's where you do, use that to make your popcorn, heat up your food. Okay. All right. So be familiar with the spectrum, where it's at: gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio wave. Okay. That is the electromagnetic radiation spectrum. Okay, 1900s. Now, recall in the last chapter, we were talking about J.J. and Rutherford and so forth. They were doing their work in the 1900s. Well, in the 1900s, another scientist, German scientist, very famous one, Max Planck, physicist, proposed an idea that was kind of controversial at the time. Okay, he suggested that energy was emitted in small bundles, in quanta. Okay, it wasn't continuous. That there was little spurts of energy that were being generated here. Okay, that was energy, and that basically saying that energy is not continuous. It's not continuously being emitted. It's coming at us with specific energy levels, and he defined that individual unit of light as a photon. Sci-fi is taken up on that term, and now we got photon torpedoes, right? They're basically just light. But if you think about it, light itself, you think, well, it doesn't seem that hazardous, but it can be. Light can be very powerful. You got laser beams that can cut right through metal and can be, pretty tough. So anyway, it's just simply light, electromagnetic radiation. So what Max Planck proposed was that these electrons we're going to learn exist in levels, okay? And you coined the term quantized. They're not continuous. Okay, how can we explain that? Well, we can explain it with this wedge on the left where you got the balls just rolling free, all continuous, okay? As compared to the stair step where the individual is climbing up, or the cartoon individual is going up the steps, where the energy level of the steps is very specific from one level, from the bottom ground level to the next level, okay? Very specific. Now, again, 1900s, Niels Bohr, he proposed that, based on Max Planck's work and other work, he proposed that electrons that are orbiting around the nucleus occupy orbits with distinct energy levels, okay? Now, up to this point, the electrons were just kind of sitting there when they weren't sure where they're at. You know, they just knew they're out there within the atom. Then, again, the protons and neutrons are in the center nucleus, but the electrons were out here someplace. And so what Niels Bohr is suggesting is that these electrons occupy specific energy levels, okay? Now, go to your periodic table. And if you go 1, 2, 3, 4, 5, 6, and 7, if you were to mark up your periodic table, okay, these numbers represent energy levels. Right now, there are 7 energy levels. The first energy level encompasses hydrogen and all the way across to helium. Then we get the second energy level, third energy level, et cetera, et cetera. Think of these like in that simulation I showed you with the dotted circles. That's the first energy level, and then you get a second one. So we have 7 energy levels where you have, let's say, the nucleus in the middle, and then you got 1, 2, 3, 4. So 1, 2, 3, 4, etc., all the way to 7 energy levels. That's what I'm trying to draw a picture, a cross-sectional picture of these 7 energy levels. Okay, and that these electrons occupy, for this particular atom, whichever atom you're talking about, occupy energy levels. Okay, with that in mind, you can see that your first trend is as follows. If I were to compare the size of sodium versus the size of potassium, the ratings, can I make a conclusion based on what I just told you of which atom is bigger, sodium or potassium? What is your thought process tell you? If I need to compare and say, okay, which of these two elements, sodium, the ones I circled here, and potassium, which one is bigger in diameter as far as size? Okay, keep it in mind that potassium exists in the 4th energy level, and sodium exists in the 3rd energy level. So what would you say, who's bigger? What does your intuition tell you? Sodium or potassium? Well, potassium would be bigger, okay? You got it, exactly. Potassium would be bigger because it exists in the 4th energy level, right? Where cesium, number 55 down here, that one would be even bigger because it occupies the 6th energy level. And so what you see in the trend in the periodic table, that as you go down the periodic table, the elements get bigger in diameter, okay? Simply because we're increasing the number of energy levels. All right, so back to Niels Bohr. So we got the Bohr atom. model where you're saying the electrons are quantized, okay, and they occupy very distinct energy levels. Okay, now keep in mind here that, you know, when we look at these models and electrons, we got to think three-dimensional. I draw pictures and diagrams here. We have, and we're showing, and that's two-dimensional, but our world is three-dimensional. So you got to think in terms of three-dimensional. Okay, so the orbits are called energy levels or shells. Both, I prefer the term energy levels because that's what they are, energy levels. Some people call them shells. That term still utilized, and there are 7 energy levels. Okay. Also, those 7 represent periods on the periodic table, 7 periods. Each energy level has a specific radius and a specific amount of energy associated with that particular radius. Okay. And so this kind of represents what the model. You have the nucleus in the center. The dotted line represents the first energy level, the second, and the third. Obviously, we don't have all 7, okay? And these electrons occupy those energy levels. Now, the question is how do we know this is the case? How do we know that we have energy levels and you know, what brought us to this point for this particular model? Well, what brought us to this point is what are called line spectra. Let me explain what happens. Bohr, in his work, basically took a lamp, like a neon lamp, put whatever element inside, and then created put energy through it and created light. Okay, just like our lights up here, you know, you got a neon lamp or some sort, okay? Then he took that light that was emitted and he localized it and ran it through a prism. That prism breaks up the light into the different wavelengths. Just like when you see a rainbow after a rain, okay, you see that rainbow, that's the light that is being broken up into the individual wavelengths, at least the visible light that we can see, and we can see the rainbow, okay? And every element he looked at emitted what we call now a specific emission line spectrum. So let me explain what happened here. Okay, so we got a gas, took some hydrogen, put it in a sealed tube here in the picture, and hit it with some electricity. When that occurs, what happens is the hydrogen electrons get excited, okay, because they're picking up energy. And so the electrons who are in, quote, the ground state, the stable state, get excited and get kicked up to the next energy level temporarily. Now, as I mentioned in lab yesterday, the conservation of matter, conservation of energy, that's all around us. So these electrons that get kicked up to the next energy level are not going to hang out up there. It's a very unstable state. They're going to come back down to their stable ground state. But in doing so, because the conservation of energy law tells us that what energy you put in has got to come out. And that electron emits that energy it picked up to go up to the next level. And it emits it as light, okay? So that tube here gets lit up. Right here. So here's the hydrogen gas. We put some electricity through it, we excite the molecules, and then we run it through a slit, and all that does, it just focuses the light and localizes it so we can run it through a prism. The prism then breaks up the light into their specific energy levels, okay? And you end up with this spectrum. This spectrum is specific for hydrogen. In fact, that's one way to identify hydrogen that's, let's say, far away in space. is we analyze the light that's being emitted and see if it has a spectrum for hydrogen, because that is the fingerprint for hydrogen, where we got these lines representing different wavelengths. NM means nanometers. We're down to the atomic scale, okay? And here's, they each have a color here. So that is the spectrum, the line spectrum for hydrogen. And if we do the same thing for a variety of different elements, lo and behold, you get a variety of different line spectrums, which again is the fingerprint for that particular element. And each line, you can take that information and back calculate, and it's a lot more complicated as I'm telling you here, but you can back calculate the lines and figure out the energy levels and figure out which electrons are going from point A to point B and getting excited. Okay, so this information really added to Bohr's model in that the electrons are in very specific energy levels. Otherwise, we wouldn't have a spectrum. It would be like one, I don't know, be like one colored bar or something, okay? But we have very specific wavelengths and lights emitted. Okay, so what is happening here, as I explained earlier, we have got the nucleus and we have an electron represented by this red dot, which occupies, its stable orbit, okay? It picks up energy. You either heat it or you give electricity. It picks up energy. It excites the electron from its ground state, its stable state, to the next level, okay? To the next energy level. Notice that distance is very specific in energy, okay? Now, that is not a very stable state for did somebody raise their hands, or was that me? I didn't realize the time. Okay, let's take a break. I got 2:40. Let's go 2:55. Okay, why don't we do that? And we'll come back. We'll come back here, 2:55, do 15 minutes. All right, so let's take a quick break. Okay, as I was saying here, what is happening to these electrons is they are getting excited to go from what we call the ground state, their stable state, and they're being kicked up to the next energy level, okay? A very specific energy level. Well, they're not going to hang out, nature being nature, they're not going to hang out the excited state very long. And so this is the excited state here, okay? And then they're going to drop back down to the ground state. And in doing so, they're going to emit energy. And it could be emitted as light, it could be emitted as heat. We see that all around us, all the lights around us, the computer that you're looking at right now, the image that you see is because the molecules on the screen are being excited, and then they're emitting light as they go back down to the ground state. We're able to see an image. If you have an electrical burner at home, you turn it on, that coil gets, very hot. And because as the electricity goes through the coil, it excites the molecules of the metal, and there's resistance in that metal. And in that case, it gives off energy. The amount of energy it gives off is given off as heat, okay? All right, so that's what's happening to the electrons, very specific energy levels. Okay, now there are 7 energy levels, as I mentioned earlier, related to the 7 energy levels, or we call periods on the periodic table. it turns out that within the energy levels, there are what are called sublevels, specifically 4 types. These are also called orbitals, okay? Now, not all energy levels have all the orbitals. And we're going to talk about energy level 1, which one it has, but they have letters, names or letters, S, P, D, and F, okay? So we have the S orbital, the P orbital, the D orbital, and the F orbital. These are sublevels within the energy level. Now, the very first energy level, which if you look at the periodic table, it starts off with hydrogen and helium, only contains the S orbit, okay? And we denote that notation by the number 1 and then the letter S. Okay? We're also going to use superscripts to describe the number of electrons within the orbits. We're not going to introduce that right now. We're just going to talk about the specific energy levels, okay, and then the suborbitals or the orbitals within those energy levels. So there's only one sublevel, one orbit within the first energy level. If you move on to the second energy level, then you have, starting from lithium on the periodic table. I hope you have your periodic table in front of you, that way you can make reference to it. Lithium on the far left, and as you go across the periodic table, goes all the way to neon, okay? There are 2 orbits for the second energy level. Now, all of the orbits 1 through 7 have the S. So we got 1s, 2s, 3s, 4s, all the way down to 7s. The P gets introduced only at the second energy level, okay? So we have the 2s and the 2p at the second energy level. The third energy level, which begins with sodium and shoots all the way across, we introduce the D orbits. Again, it does have the S. So you can see a little trend here. Hopefully you get the 1s, 2s, 3s, and those particular orbits have a particular shape. We're going to talk about those. So they can have circular shapes. So the 1s is kind of small, 2s is bigger, 3s is even bigger, 4s, 7, all the way to the 7s, okay? At the third energy level, we introduce the D orbits, okay? So we have, starting with sodium going across the periodic table, we have the 3s, the 3p, and the 3d. Then we have one more. And at the fourth energy level, we introduce the F. So like the previous energy levels, there's a 4s, there's a 4p, and there's a 4d, and then we introduce the new one, which is the 4f, okay? All right. And we can continue down to the 5th, 6th, and 7th, but we're gonna just stop it here at the 4th, okay? Now, this kind of shows you here, if we were to draw a 2-dimensional model where the circle represents the energy levels, energy level 1, 2, 3, 4. So the very first one only has the S, the second energy level has the S and the P orbits, third has the S, P, and the D, and the fourth energy level has the S, P, D, and F orbits, okay? Now, what these orbits represent, what they represented was these mathematical equations, very complex mathematical equations to describe a region in space where it is predicted that there should be an electron, okay? And if you take these mathematical equations and you plot them 3-dimensionally, you end up with a picture of what that orbit looks like, okay? So, and we're going to have some pictures here to look at in a moment. Now, what was determined was this. For the S orbits, okay, there's only one orbit for the S. Now, every orbit, regardless if it's S, P, D, or F, can handle a maximum of 2 electrons. Since there's only one S orbit, a maximum number of electrons for all the S orbits is 2. Okay. Once the S gets full, you start putting electrons to the next orbit, which is the P. Now there are 3 P orbits, and every P orbit can handle a maximum of 2 electrons. So for all the P's, there is a maximum of 6 electrons. Okay. The D, there are 5 orbits for the D. Again, 5 orbits, each one can handle 2. The maximum number of electrons that I can put into any D orbitals is 10. And then finally, the F orbits, there's 7 of them. 7 orbits of all different shapes. I have a picture here of their shapes. They're kind of crazy looking orbits. And each orbit can handle a maximum of 14 electrons, okay? 14 electrons. All right, so the way we represent that is these boxes. Now, actually, this picture should be inverted. You know, there's an upside down pyramid where you got the first energy level with the S, and then the second energy level with the S and the P, okay? Because that's what we're doing. As we fill up the electrons to the atoms, we start first with the lowest energy level, and then we add, once that lowest energy level is full, we move up to the second energy level and fill up those orbits until they're full, and then go on to the third. So that's what I mean by this probably should be better represented if this was an inverted pyramid. Okay, now, with respect to the energy level, since the the first energy level, you only have S, there's nothing else. That's just one orbit, that's it. But if you look at energy level 2, you have the S, and then you have the P. Now, with respect to energy, the S is a lot lower in energy level than the P, which means is that you start filling up the S orbits first before you fill up the P's, okay? And then the third energy level, you introduce the D. Now, if you look at the box here for the P, there's 3 boxes because there's 3 orbits, and each box can handle 2 electrons. If you look at the D in the third energy level, there are 5 boxes, and each one can handle 2 electrons, okay? And in the D, there are 7 boxes. Now, as we fill up electrons, and we take the very first electron, which is hydrogen, I can represent that by an arrow, okay? That arrow represents an electron for hydrogen. Hydrogen has 1 electron. It occupies its orbit in the 1s superscript 1, okay? Now, when I go across the helium, I draw another arrow, okay, because helium has 2 electrons, and I have to fill up the s orbit first. So I got 2 arrows representing helium, representing 2 electrons, okay? And they're in opposite direction because one of the rules of the orbit of electrons within an orbit is there's 2 per orbit, but they circumvent the nucleus in different directions, opposite directions, and that's why I draw the arrow opposite. All right, so that would be represented by one S superscript 2. What that states is this, and this would be for helium. Okay, helium has 2 electrons. Its electrons occupy in the first energy level and in the s orbit, and that superscript says I got 2 electrons there. okay? Now, if I move on to the next one in the periodic table, that's lithium. Lithium has 3 electrons, okay? With 3 electrons, I first fill out the s orbit. So there is 3 electrons there, okay? The 2 in the first energy level, and then the 1s1, 2s1 for the second electron. Lithium has 3 electrons. 2 of those electrons occupy the first energy level, and then the third electron occupies the next energy level. I can't put the third electron in the first energy level because the first energy level is full. Okay, those orbits are full. So I got to go to the next energy level. Okay, and that is lithium. For beryllium, right next to it, the next one has 4 electrons. So I fill up the s orbits first. Okay, because they are lower energy level before I start jumping on the p. So think about it. Beryllium has 4 electrons. If I wanted to show its electron configuration, it would be 1s2, 2s2. Okay, that is how I would write the electron configuration for beryllium. Okay, beryllium has 4 electrons. Of those 4 electrons, 2 of them occupy the first energy level, the s2, 1s2, and then the second energy level, also in the s orbit, are the next 2 electrons. Okay, and then if we go across to boron, guess what? Now we start occupying the p orbits. See, boron has 5 electrons. I got 5 arrows there. You see that? And if I continue across the periodic table, well, first of all, I continue to go with the arrows I fill up each individual orbit first. So I go carbon, that's carbon, because carbon has 6 electrons, right? 6 electrons total. Of those 6 electrons, 2 of them are in the first energy level, and the other 4 are in the second energy level. Of those 4, 2 of them occupy the s orbital, and 2 of them occupy the p. Okay? Now continue across to nitrogen, and we fill up the next box. Nitrogen has 7 electrons. Is there not 7 orbits, 7 arrows there? Yes, there are. 7 electrons. This represents, let me erase this other so we don't get it all confused. Okay. 1, 2, 3, 4, 5, 6, 7 for nitrogen. Now we start filling up the rest of the P. So we go across nitrogen's oxygen. So now we can go to the other P and start filling that one up. Okay. Oxygen has 8 electrons. 2, 4, 6, and 8. Okay. Those 8, 1, 2, 3, 4, 5, 6 of them are in the second energy level, right? 2 of them happen to be in the s orbit, and the other 4 happen to be in the p, and that's oxygen. And now we got fluorine. Notice it's all sequential. Just go across, just fill up the orbits as you go across the periodic table for every element. This is fluorine. Fluorine has 9 electrons. There should be a total of 9 arrows there, okay? And then finally, the last thing is neon. Neon, let me draw this. Neon, its electron configuration can be written as 1s2, 2s2, 2p6. That was helium up there, okay? Because neon has 10 electrons. of those 10 electrons, 2 of them occupy the first energy level in the s orbit, 2 of them occupy in the s orbit in the second energy level, and then 6 of them are occupied in the p orbits of the second energy level. So I needed to write the electron configuration. That's how I do it. That's the electron configuration for neon. I got 1s superscript 2, 2s superscript 2, 2p superscript 6. Now, notice something interesting about neon. This is neon. Element number 10. Okay. If you look at its position on the periodic table, neon occupies that last column of the periodic table. That last column has their own very specific name. They're called noble gases, okay? They're noble gases is because they're very unreactive. And keep this in mind, whenever there's a reaction, it's all about electrons, okay? Electrons are moving from one point to the other, unless the orbits are full. Once the orbits are full, and this magical number is obtained, it's called, and that number is 8. The octet rule has been fulfilled. You get a material that's very, very unreactive. And so note the number of arrows on the second energy level, okay? There's 8, okay? Of those 8, 2 of them are in the second S orbit, and the other 6 are in the 2p orbit. But there's 8, okay? All the orbits are full. There's no more room for anything else, okay? And so it's a noble gas configuration. It's not going to react, because for things to react, I'm going to have empty spaces to either put electrons in or take electrons out, okay? Now, that's neon. If we go to the next configuration, not next configuration, we go to number 11, which is sodium. Sodium has 11 electrons. And where's that arrow go? Obviously, it's going to be in the third energy level, because it can't go anyplace else. It has to go to the next energy level, okay? And that's in the third energy level. All right. And this procedure continues as you go across the periodic table. That's sodium, okay? Magnesium, right there. All right. I shoot across to aluminum, right there. Silicon, right there. Phosphorus, right there. Okay, then we got chlorine. Oh, should be sulfur, and then chlorine, and then the noble gas argon. Okay, and that's argon. And if you look at argon, again, it is in the last group again, in the very last group, and there are 8 electrons in their outermost shell. I'm going to refer to the outermost shell as give it a name called valence electrons. The valence electrons are the outermost shell. A lot of these atoms have multiple shells. Okay, and if the outermost shell is full with that magical 8, then it is very unreactive. It will not react with anything. Any other configuration where it's not full, things are going to happen. Okay, either electrons are going to be lost or electrons are going to be gained. All right. Okay, so let me do this here real quick. Let me call up my bear with me for a second. All right, here are we at? Okay, I have a special periodic table that you may want to okay. You may want to label your, give it a second, I was trying to load up your periodic table. All right, let me share. The periodic table that I have here is as follows. Okay. Now, recall that we mentioned we have the s orbit, we have the d orbits, we have the p orbits, and we have the f orbits. Now, if you take your periodic table and if you were to label them as follows, it will help you to do the electron configuration. Okay, notice something here. The periodic table, there's Roman numerals on top. We got the 1A, 2A, then we should jump across to the 3A, all the way across to the 8A. Now, those Roman numerals will help you with information, okay? But until then, let me give you this information. The first two columns, 1A and 2A, all the way down, okay? That one and this one. Think of those as the S elements, okay? S elements. Now, what they have in common, being in the same group, is the number of valence electrons. So if you look at hydrogen and all the way down to cesium, or the last one, number 7, what they all have in common is there's one valence electron in the outermost shell, okay? The next group has 2 valence electrons in the outermost shell. And being depending on the energy level it is, that would be the S2. So for beryllium, to describe the S electrons would be 2s2 because it's in the second column. Okay. Now go across here and go to starting with group 3A. Notice something that we have 6 columns, 2, 3, 4, 5, and 6. Okay. The noble gases are in the far right, and they have the Roman numeral 8, which represents the 8 valence electrons, that magical 8, and therefore very unreactive. Okay. If you look at that back to the first 2 groups, the Roman numeral represents the number of valence electrons. So everybody in group 1A has 1 valence electron. Everybody in Roman numeral 2A has 2 valence electrons. What about 3A? What does your intuition tell you? How many valence electrons does everybody in group 3A have? Given the trend that I just explained here for Roman numeral 1A and 2A. How many valence electrons would 3A have? Exactly 3, perfect. And 4 will have 4, 5 will have 5, etc. Okay, until you reach the last column, which would be 8 valence electrons. The only exception in the last column is helium. Helium has its own special rule. It's a duet rather than the octet because it only has 2 electrons. It can't have more than, it is nowhere near the number 8. It just doesn't have those electrons, okay? So all those, the driving force in the chemical reactions is to get to that magical 8, to either lose electrons so that your new valence shell has 8 electrons, or gain electrons, so your new valence shell has 8 electrons, okay? But more on that. And notice something here, there's 6 columns. Think of these 6 columns starting from 3A to 8A as the P elements. So if I'm starting to fill up the electrons, it would be P1 in 3A group, P1, P2, P3, P4, P5, P6, okay? The number in front would be depend on the energy level they're at. So it could be 2P, 3P, 4P, depending. But going across the periodic table, you would know how to fill it up. Boron would be P1, okay? Specifically 2P1, because it's in the second energy level. All right, 2P1, then carbon would be 2P2, etc. All right, now look at these other metals that are called B, Roman numeral B, okay? If you count the number of columns, you're going to find 10. I'm going to just continue there. 10 columns across here, okay? And that's the D. Remember the D elements? There's 5 orbitals. Each one can handle 2 electrons. So I have a total for the D. The maximum number of electrons for the D orbits would be 10. Okay. And then finally, the F elements, which you see here in the bottom. If you count the number, let me change the color here so we can see. There are, from here to here, there are 14 columns. F1, F2, F3, F4, F superscript 5, all the way to F14, okay? The point of this exercise is this: when we do the electron configuration, you can just simply utilize the position of the element on the periodic table, keeping in mind what type of element that is with respect to the orbits, S, P, D, and F, and what energy level. You can very quickly write the electron configuration. Or you can sit and memorize what the book gives you and memorize a sequence, which sometimes can be challenging, okay? But I tend to want to use the periodic table because very quickly you can do electron configuration. Keeping in mind is S elements, D elements, P, and F. All right. Let's go back. So we've been talking about the different orbits, okay, and how we fill them up. And we start to fill them up. And the electrons, every box here represents, one box represents the orbit. Every box can handle a maximum of 2 electrons within the box. For the P's, there's 3 boxes or 3 orbits. For the D's, there are 5 orbits, okay? Hence, I can put in 10 electrons for the T orbits. And the F, there's 7. I can put in a maximum of 14, which correlates to the periodic table where we got S1, S2, and then we got P1 all the way to P6, and then we got D1 to D10, and then F1 to F14. Okay. So the fascinating part about that is that this model kind of, I don't know what came first, the chicken or the egg, with respect to the periodic table and the position of all that. And then the model came into play and it just kind of fit based on, why certain elements react the way they do. If we look at the periodic table again, sorry about that, my dog's playing with his toy. If we look at the periodic table again, as I stated, for the A elements, the Roman numeral A elements, that represents the number of valence electrons within that group, okay? And so lithium, which is, let me see if I can zoom this up a little bit more. See, lithium and sodium and potassium, okay? What they all have in common is hydrogen, lithium, sodium, all the way down to number 87. What they all have in common is they all have one valence electron in the outermost shell. Okay. Hydrogen has one electron. That's it. That's the one electron it has. Okay. Lithium has 3 electrons, but 2 of them are in the second energy level, and then that one single one is in the first energy level, excuse me. And then the second one is a 2s1. So this would be 2s1, 1s2 for lithium. Okay. Sodium again has 11 electrons total, but one of them is in the outermost shell, specifically the 3s1 level. It's in the third energy level. Okay, it's in the s elements of first column. Potassium has 19 electrons, but the one valence is in the 4s1. Notice the trend: 2s1, 1s1, 2s1, 3s1, 4s1, etc. And they all have one valence electron. And all of them, the reason they're in the same group is because they react very similar. And now we know why, because they got one valence electron. It's all about the electrons causing the reactions. Okay. The periodic table we're going to learn was put together by a scientist, again, old guy, 1800s, because what he did, he grouped them together based on their reactivity. He knew that the elements of what they knew what existed, they reacted very similar, so he grouped them together. Unknowingly, this is why they do that, because they had the same number of valence electrons. Everybody in group 2A has 2 valence electrons in the outermost shell. Yes, they differ with respect to total number of electrons, but they have in common the same number of the outermost shell valence electrons. Hence, they react very similar, okay? Because of that. All right, so let's take a look at some of the shapes. Now, if you look at the s orbits, and this is from 1 through 7, s orbits, is once you take, these come from mathematical equations, big old mean looking equations, and you plot data in them, you get a picture that looks like this, okay? A 3-dimensional picture, because remember, we live in a 3-dimensional world. And what that represents is the probability of the electron being in that dark area, okay? And it has circular shape. These are the s orbits. The p orbits, there's 3 of them, have what are called the dumbbell shapes. There's 3 distinct orbits, okay? Remember, 3 p orbits, each one can handle 2 electrons. And that's their particular shape. If we look at the Ds, okay, look at the one on top is the S. Keep in mind, we got from 1s, which is the first energy level. And as we go down the periodic table, we got 7s, okay? The s orbits are common in all 7 energy levels, and they're all circular. The only difference is you start off with the 1s is, this size, and the 7s, size of a beach ball, okay? But it's still round. The same is true with the P. You start off with the 2p, that's the second energy level when they get introduced, all the way down to the 7. And the only difference is the 2p, the 3p is they're bigger in size. Where the shape gets a little crazy is when we get into the D's and the F's. And these are the general shapes of these orbits, very exotic looking shapes. Okay, the D's in blue there, there's 5 of them in the different axes, and each one can handle 3 electrons. And then you got the green which represent the F orbits. You know, these come from mathematical equations to explain, you know, how the model of our elements. A lot of scientists were not too happy with this model. The model explains a lot what we observe, okay? But on the one hand, especially Einstein wasn't too keen on this model, because on the one hand, we talk about very specific energy levels, you know, being quantized, and then we talk about the probability of an electron being someplace. And Einstein didn't feel that nature, you know, was dealt with probability. It was more like everything's exact. There's a number for it. But nevertheless, until such time that a new model pops up, this is the best model we got at this time. Okay. So anyway, there's some crazy looking orbits. All right. Now, we're going to learn about how to write the electron configuration for the elements. In other words, how to write 1s2, so on and so forth. You can memorize this table, and that's the order given to you. 1s2, 2s2, 2p2, 3s, you know, whatever, 3p, 4s, etc. Remember, in the orbit, the superscript represents the number of electrons for that orbit. Keep it in mind, there's a maximum of 2 for the S, maximum of 6 for the P, and 10 for the D, and 14 for the F, okay? And that's a particular order to do that. I tend to use the periodic table and its position to very quickly figure out its electron configuration. Let me give you an example of what I'm talking about. Let's let's, for example, do boron. Okay. So boron's right here. Okay. All right. So the first thing I do is once I find its position in a periodic table, I look and see two things. One, it's in group 3A. Okay. So that tells me that there are 3 valence electrons in the outermost shell. It also has a total of 5 electrons. Okay. So it is in the second energy level, okay, which means that the first energy level is full. So I can very quickly write 1s2, okay, because those electrons of the 5, 2 of them fill up the 1s2 immediately. Then as I go across the periodic table, as I shoot across the periodic table, this is second energy level, so I know that the 2s2 level is full. And then I start with the P. So this is the 2p. I'm in the first column, and that is 1. First column of the piece. And that is the electron configuration for boron. Okay. Now, also, if you look at the valence electrons, that means the outermost shell, which is the second energy level. The superscripts tell me there's 3 electrons, which corresponds to being in the group 3A. Okay. If I were to do the next one over, which is carbon, I would simply make that 2p into a T, 2p2. That's carbon. Nitrogen, 2p3, etc., just going across the periodic table. Once I got neon done, I start off with sodium. That tells me I am in the third energy level, 3s1. Okay. So that's usually the periodic table. It takes a little practice, but I feel that knowing its position and knowing about the S and the D elements and the F elements, etc., you can very quickly figure out the electron configuration. Or you can go ahead and memorize it. Okay. Now, here's the confusing part with this: is the D elements. The D elements start off in the third energy level. but they don't come into play until you actually start off with number, let's say 21. Okay, these are the D elements, okay? Now what happens is this. Number 21 is in the fourth energy level. But mathematically, the D orbits don't not, you would think it would be 4D, right? 4D1 to explain that, but it's not the case. The D orbits for the elements in period number 4 actually begin in the third energy level. They are one energy level lower than where the elements are. And that's why you see the 3D come into play. But you don't have to worry about them until you come to element number 21, okay? The next element down here, Y, its D would be 4D. So you just subtract 1 from the period that it's in. And what's even more confusing is if you look at these guys, you would think, you would think it's in the 6th energy level, you would think 6F1, but it's not the case. Like the case of the D, where the energy level is 1 energy level less, the F elements, the F energy levels are 2 energy levels less than the energy level that they're in. Okay, and so down here, where we have start the F, F1 and all the way to F14, it is not 6F1, it's actually 4F1, and then 4F2, 4F3, all the way down to 4F14, okay? So the F energy levels are 2 energy levels less than the energy level that they're in. The Ds are 1 energy level less than the energy level that they're in, okay? And that's just brought to you by the mathematics of this, this quantum mechanics. The mathematics involved are quite extensive, quite extensive. Okay. All right. So for example, doing carbon is, go back to the product table. Okay, carbon's right here. Here's carbon, 6. Let me zoom up a little bit. 6 electrons, okay? It's going to have, guess what? 4 valence electrons, because it's in group 4. All right. It is in the second energy level, okay? So the first energy level is full, so it's 1s2, and then we're going across the periodic table, so those electrons get full 2s2, okay? And then we get into the P, we're in the second column, that is 2p2. Oh, not 6, I got jumped ahead. 2p2, it's in the second column, okay? Also look, the valence shell, which is the second energy level, has a total of 4 valence electrons. 2 of those 4 are in the 2s orbit, and the other 2 are in the 2p orbit. But there's a total of 4, which is consistent with the group Roman numeral 4a. And that is true for all the elements down in the same group, okay? All right, so very quickly, that's how you can do electron configuration. If I did nitrogen, which is right next to it, I just make that 2p3, and there you go. Or if you're comfortable with just memorizing that, then feel free. Okay, whatever works best for you. but it takes a little practice. So I would suggest just arbitrarily, pick some real simple, be able to do at least up to the first 20 elements. See if you can write the electron configuration. You're going to see once you start off, it's just a matter of sequential adding the energy levels in the orbits. It's not going to be that complicated. Okay. I will do some more maybe during the lab period if there's any questions about how to do electron configuration. Okay. So like I said, be able to do at least the first 20 elements. Okay, here is electron configuration for carbon. 1s2, 2s2, 2p2. Remember, the coefficient represents the energy level, and the letter represents the orbit, and the superscript on the letter represents the number of electrons in that orbit. Okay, keeping in mind that s orbits can handle a maximum of 2. P orbits can handle a maximum of 6, D 10, and F 14. Okay, now, so going back to this, for the third energy level, okay, for the third energy level, what is the maximum number of electrons that I can put in the third energy level? What do you think? Given this diagram here. Well, let's jump ahead. Let's go. Let's keep it simple here for right now, and then we'll move forward. For the first energy level, what is the maximum number of electrons that I can put in level number 1? 2, exactly. So 2 is the max. Where's my, come on. 2. What about the second energy level? What is the maximum number of electrons that I can put? What do you guys think? Okay. Yeah, we got it. Yeah, 8, exactly, because I can put 6 in the P and 2 in the S, so the maximum is 8. And what does that tell me about the third energy level? Would that be 18? That would be correct. And then the last one? What about the last one? Maximum number of electrons I can put in the fourth energy level. And that would be correct, 32. Okay. And so be aware of questions like that, where they say, okay, for the third energy level, what is the maximum number of electrons that I can put in the third energy level? Not to be confused with what is the maximum number of electrons that I can put in the d orbit? What is the maximum number of electrons that go into the d orbit? Okay, that is correct, 10. All right, so be aware of the questions and how they're asking, what they're asking for. All right, this one here, I talked about the maximum number for a specific energy level. Okay, and not to be confused with the maximum number of electrons for a specific orbital. Okay, this is basically what I was showing you with respect to count them as the S. Think of these elements, the first 2 as the S elements. We got the yellow as the P, Okay, remember the P, I can put in 6 electrons. So going across, starting with group 3, I can go P1, P2. Let me do it this way. Here I'll go S1, then over here S2, and then from here D1 all the way to D10. Then here I got that's P1 all the way to P6, and then obviously F1 to F14. And, depending on where it's at, like silicon, we can very quickly figure out the electron configuration for silicon based on its position on the periodic table. Okay. And it's a matter of just writing the coefficients and the number of electrons. Okay, so we have sodium, which is 1s2, 2s2, 2p6, and 3s1. Okay, oxygen, 1s2, 2s2, 2p4. Okay, calcium is 1s2, 2s2, 2p6. I'm going across the periodic table, and then I shoot around to the third energy level, which is now 3s2. And then and then 3p6 and 4s2. Okay. Then finally chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. Okay. All right, and those are electron configurations. And basically, notice what they all have in common is everybody fills up the 1s2, then the 2s2, and then the P could fill it up, or it depends on which element it is, and you just go sequentially. Okay, this one here kind of shows you the configuration, okay, for the element. Now, notice something here that is for the D's. It's not a straightforward 1, 2, 3, and 4. For us, Chem 130. It's a straightforward D1 to D10. Okay, notice that it does change around a little bit in reality, but we're not too concerned about it for 310. And that's also true for the F, sequentially F1 through F14. Notice that there's a lot of things to explain that, but we're beyond the scope of Chem 130. Okay, but that one there helps you with the electron configuration, knowing its position on the periodic table, all right, or using the sequence that the book gives you, whichever works for you. Okay, and this is kind of like, all right, if I were to do aluminum, okay, so aluminum is 3p1. Now, okay, I can go 1s2, 2s2, 2p6. I've gone all the way across there, and then across to neon, and then I go 3s2 right here, and then 3p1. See how quickly? 3p1 right there. All right. All right. Now, noble gases, the book uses the term a lot, happy. Okay. All right. Noble gases are happy. Okay. I prefer the term stable. Just leave it at that. And they're stable because the outermost shell has the magical 8 number. Okay. The octet rule has been fulfilled. And so being stable means that they're not going to react very readily. It's going to be difficult for these guys to react. Doesn't mean they're not. I'm just saying it's going to take energy. If you want to get them to react, it's going to take some coaxing, because their outermost shell is full, their valence shell is full, all the S and Ps, everything's full, okay? Helium, again, doesn't have the magical 8, has their magical 2 as a duet rule versus an octet. Okay, that configuration where you have a S2, P6, regardless of what is second energy level, third, fourth, or fifth, that's a very stable configuration, okay? Because there are 8 valence electrons. Just like for helium, it's a configuration is 1s2, as far as the electrons are concerned. Very stable. So as we stated earlier, the valence electrons are the outermost electrons in the outermost level. And that's where all the, it's, reactions occur because of the electrons. That's where all the actions happen. The outermost shell is either an element either going to lose electrons or gain electrons. It depends on the type of element it is. And that's where all the action, so to speak, I should say, chemical action that is there in the outermost shell. Okay. The core electrons, those are the ones inside. They're not going to do anything because one, they're full. Okay. Plus they're inside. So they're not doing anything compared to the outside. So if we look at phosphorus, here's the electron configuration of phosphorus. 1s2, 2s2, 2p6, 3s2, 3p3. Okay. If you look at phosphorus, phosphorus is in group 5A. Okay, look at your periodic table, you see it. Phosphorus is in group 5A. That should tell you that it has 5 valence electrons. Okay. And if you look at the electron configuration, the valence electrons are denoted here in, I guess, purple color. There's 5 of them. Okay. 5 valence electrons. 2 of them occupy the s orbit, 3 of them are in the p orbits. Okay. All right, there are 5 valence electrons. Now, I might as well give it to you now, okay? So you can start thinking about it. If we look at the periodic table, come on, periodic table. If we look at the periodic table, and specifically look at group 4A, okay? Everybody in that group has 4 valence electrons, okay? This is our central point, so to speak, okay? Now, the object here is to obtain that magical 8. And that's either going to happen by either gaining X amount of electrons or losing X amount of electrons. Now, when it comes to group 4A, those guys are on the fence. It takes same amount of energy to lose 4 electrons as it would to gain 4 electrons. So the chemicals, the elements in group 4A can lose those 4 or gain them. They can vary, okay? And that's our little benchmark to point to. It depends on the conditions, okay? That means that group 5 to 7, guess what? They are going to gain electrons. Why? Because group 5 has 5 valence electrons. It only needs 3 more electrons to get that magical 8. Group 6 is only 2 electrons away from the 8. And group 7 is only 1 electron from that magical 8. Okay? And so those chemicals tend to gain electrons. And those chemicals are non-metals. We're going to learn about who's a metal and who's not a non-metal. On the other spectrum, once we get to group 3A, we started at 4A. 4A is our top of the fence, but anything less than 4A, lose electrons. So everybody here, group 1 and group 2, guess what? They're going to lose electrons. The ones in group 3A are going to lose 3. Because think about it from an energy perspective. I got 3 valence electrons. I need to get to 8. That means I got to pick up 5 electrons. From an energy perspective, that's pretty tough. Now, can it happen? Could, maybe, but probability not too high. It's easier from an energy perspective to lose 3 than to pick up 5, okay? And to try to maintain 5 to give you that magical 8. It's not very stable. So metals tend to want to lose electrons because what's happening when they lose electrons, then the next level in has the octet. The same is true for the nonmetals. When nitrogen, for example, gains 3 electrons, it went from 5 valence to 8. It picked up 3 electrons and now has that magical 8. So now it's a lot more stable, okay? And that's the driving force for these chemical reactions. All right. Is that magical 8. All right, so question here is asking you, well, how many valence electrons do these elements have? All right, so you just need to find them on the periodic table, look to see what group they're in. And this is only true for the A elements, okay? The B elements are not as predictable. They can vary. You can't predict how many electrons they're going to lose. Some of the B metals can lose 1, 2, 3, 4, maybe even more. It's difficult to predict, but we can predict the electrons and the number of valence electrons from the A metals. So chlorine is has the following electron configuration: 1s2, 2s2, 2p6, 3s2, 3p5. It has 7 valence electrons. 7. And think about it. It's only 1 electron away from that magical 8. So chlorine will be predicted to gain electrons. And when it picks up an electron, guess what? It picks up a negative charge overall. Because prior to it, chlorine is balanced. Chlorine has 17 protons, 17 electrons, okay? When it picks up 1 electron to give you the octet, it now has a net -1, all right? Beryllium, 1s2, 2s2, has 2 valence electrons. It's in the second energy level. It will lose those 2 electrons, okay? Aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. The valence shell is in the third energy level. 3 valence electrons, okay? 2 of them are in the s orbit, 1 of them is in the p. But it will lose 3 electrons to have a +3 charge when it's done. I mean, before I leave this topic, think about it, okay? When aluminum loses these 3 electrons, look at the new valence shell. It's in the third energy level, okay? And now aluminum has a +3 charge. This is an ion. This is the metal. It has 3 valence electrons that it wants to readily lose, because now by losing those 3, my new valence shell is in the second energy level, and I got 8. So plus I got a +3 charge now, an ion. All right, so the group number, the Roman numeral number, will assist you with respect to the number of valence electrons. And again, this is only true for the A, the ones that are the Roman numeral A elements, okay? Because the B's are unpredictable. So group 1A one valence electron, group 2A, two valence electrons, 3A, three valence electrons, four valence, etc., till you get to group 8A, Roman numeral 8A, which tells you there's 8 valence electrons. Okay. Group 4 is, again, the fence. It's on the fence. It can gain 4 or lose 4. Right. That's like a little benchmark. So anything less than group 4 loses electrons. Anything greater in group 4 gains electrons. Okay. All right. Oh, excuse me for a second. Deal. All right. Of course, helium, again, I can't overemphasize, helium has 2, simply because that's all the electrons it has. Its rule is the duet, not the octet. So question here says, well, how many valence electrons do these elements have? And to answer that, you find them on the periodic table. Strontium has 2, it's in group 2. Bromine is in group 7. Okay, so it has 7 valence electrons. Argon is a noble gas, therefore has 8 valence electrons. Silicon is in group 4A, 4 valence electrons, and sulfur has 6 electrons, valence electrons. Okay, question is, why do atoms want to make compounds? Why is it that they bond? Okay, why is there chemistry involved? Period, in general. Okay, and I mentioned it earlier. Is the driving force is to have their octet fulfilled, and they're going to do that by either gaining electrons or losing electrons. Okay. I try to demonstrate that by electron configuration to show you, how many electrons it's going to lose and how many it's going to gain. Okay. So when they do that, remember all the elements are neutral in charge because they have a equal number of electrons and protons. But when they lose or gain electrons, they are no longer elements. They are now ions, okay? And so these ions are either going to be negative charge ions or positive charge ions. If they're negative, it's because they gain electrons. If they're positive, it's because they lost electrons, okay? And we're going to talk about the charge. The magnitude of charge can vary from a +1 to a +2 to even a +3. And for the other end, the negative charge can start at -3, -2, or -1. Okay, all function of how many electrons have gained or lost. And that's where we talk about ion formation. So if we look at sodium, okay, sodium has 11 protons and 11 electrons, the element. Its electron configuration is 1s2, 2s2, 2p6, 3s1. I highlighted the valence shell. It's in group 1. It's got 1 valence electron, okay? And it's going to lose that 1 valence electron. So when it does that, now it has 11 protons and 10 electrons. Okay? Look at the net charge now. I have a net charge of +1 because I got one more positive than I have negatives. Before they balance each other out, 11 and 11. Now it's 11 and 10. Okay. Its electron configuration is now 1s2, 2s2, 2p6. What happened is that 3s1, that 1 electron they had on the outermost shell is gone. That electron's gone. So now that orbit is empty. And the new valence shell is in the second energy level. And guess what? There's 8 valence electrons in the new valence shell right here. There's 8 VEs, valence electrons. Okay. Up here, they had one valence electron. Here now they got 8, that magical 8. Okay. And it formed an ion, and now it has a plus charge. That is what you put on your French fries, the sodium ion. Okay. You would not be putting sodium metal on your French fries because it wouldn't be a pretty picture. Get pretty hot and actually blow up. Okay. All right. So let's take a look at sulfur. Okay. Well, sulfur, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. Now, if you look at the periodic table, you would find that sulfur is in group 6a. Okay. And it has 6 valence electrons. 2 of them are in the s orbit and 4 of them are in the p orbit of the 3rd energy level, shown here in bold. Okay. Now, when I talked about earlier, I said group 4 can lose or gain those 4 electrons. Depends on the conditions. That was our reference point. Then I said anything less than group 4, we're going to lose electrons. Anything greater with respect to the group number, we're going to gain. Well, if you look at the number of valence electrons sulfur has, it's 6. How many does it need to get that magical 8? How many electrons does sulfur need to get to the 8 octet? 2. Okay, it's going to pick up 2 electrons because it has room for 2, specifically in the 3p4 region. Okay, there's room for 2 electrons in there. And in doing so, now it has a full octet. Plus, it has a -2 charge, okay? Because it started off with 16 protons and 16 electrons for a net charge of 0. When it gained those 2 electrons, it went from 16 protons to 18 electrons. That means I have an excess of a -2. So my overall charge will be a -2, okay? And my octet now is full and becomes very stable. Because the ultimate goal is stability. And it wants to be more stable either by gaining or losing electrons. Okay, and you'll see here that we're going to learn about sodium. Sodium is a metal where sulfur is a nonmetal. And I mentioned earlier that nonmetals gain electrons, metals lose electrons. All right, here they're asking you to write the electron configuration, which hopefully you just knock it out, but be careful, okay? Look at the charges on these here. I want you to write the electron configuration of the ions and not the elements themselves. Okay, so potassium has lost 1 electron, so its new electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6. Okay, it has the same number of electrons as argon. Okay. It is what we call isoelectronic. Isoelectronic with argon, meaning they got the same number of electrons. I did not say that potassium ion has become argon. Okay, I didn't say that. I said potassium ion has become isoelectronic as argon because now they share the same number of electrons. Because for potassium to become argon, we gotta lose some proton, lose a proton. That's not gonna happen. Okay. N3 N3 means that it picked up 3 electrons, nitrogen did. Okay. Its new electron configuration is 1s2, 2s2, 2p6. Look at the valence shell. The valence shell is nice and full, happy with the happy 8. So now N3 is now isoelectronic with neon. They share the same number of electrons. And then potassium, by losing 2 electrons, because now it has a plus charge, now it also is isoelectronic with neon. Okay, they share the same number of electrons by losing 2 electrons. That is magnesium metal, whereas nitride gained 3 electrons. Excuse me, nitrogen gained 3 electrons to become isoelectronic with neon. Okay. Let's do this. Let's stop it here. Slide 29. All right, let's stop it here. I will upload this as soon as it converts. And we'll just stop it here.